Okay. $42. Okay, I should get started. All right, let's get started. Ready? Yes?
Yes, except that I'm filling out a fixed name. I'm listening.
Okay. All right, so let's see, no homework due this week. There's a lab 4, I think, right? Lab 4 is due tomorrow. Lab 5 will be posted shortly after the last section tomorrow, and then it will be due the following Tuesday. Not next Tuesday, but the following. A 2-day lab. So you get 2.5 weeks for lab 6, but the people have been known to be done in 2 days. Yes? I think they sleep. They just basically, besides sleep and eating, they work on lab 6. All right, anyway, so any questions before we continue talking about state minimization? No questions. Okay. All right. Here we go. If I can find the PowerPoint. Okay. So on Monday we had talked about state minimization. So when you design your state machine, you may want to design it in a way that you feel confident that it does what you want. And then you may discover that maybe you use too many states, that some states are equivalent. And by minimizing the number of states, you can assure yourself that you will still have the functionality that you intended and yet have the fewest number of states possible. Okay, so let's go over this again. So the method, if we're given a state machine, a state diagram or a state transition table, we can check whether there are equivalent states or redundant states using Moore's method. So the idea basically is all states are equivalent. Do you have a question? No? No. Okay. All states are equivalent. And then we start to separate them when it becomes apparent that they are no longer equivalent. So the first clue that two states are not equivalent is they have different output. So if their output is immediately different, they need to be in separate groups. They're no longer equivalent. Then the next step is two states are not equivalent if they have next states that are not equivalent. So what we do is we look at each group, and for each state in each group, we identify what groups the next states are in. Okay? And we do that for every state in every group. And then we go back and look at each group and say, well, are there states in this group that have next states that are not equivalent? And that then lets us refine that group, break it down. And groups then can become subgroups. They get split apart. And if that happens, then we have to repeat a process. And we keep doing it until we get to a point where after step 3, we don't create any new groups. And if you don't create any new groups in step 3, there's no point in repeating step 3. You'll never get any new groups, right? So you're done. And basically it means that if two states are in the same group, they are equivalent. And two states are in separate groups, they're not equivalent. Okay, so how would this be useful? So let's say we are tasked with generating a state machine or sequential system that recognizes the pattern 1000 or 0110. So either pattern. Okay. And so I'm fairly certain that this circuit does the trick, because all this that happens here is I remember the last 3 inputs, and then I have one AND gate that's recognizing 1000, and another AND gate that's recognizing 0110, and then I take the OR and I output a 1 if I have either of those patterns. Okay, now I'm 99% sure that this is correct. The question is, does it have the minimum number of states? And the answer is no. We could do this with fewer states. I don't actually need to remember all the different past inputs of length 3. So how do we get the minimum number of states? Well, we use the algorithm. Here's the state transition table. We could draw a bubble diagram, but in this case, it's easy to make the table, because what we'll do is I'll call this one Q2, Q1, Q0. So when I put them in the table, they go left to right. And then this shift register, what's in the shift register is essentially my state. That's what it remembers about the past inputs. And so the next state, well, X will become the first bit of the next state, and then we will lose Q0. Right? Because all we're doing is we're shifting in X and we're forgetting Q0. Q0 falls off the end. So you can see all these next states start with 0, and all these next states start with 1. And basically, we just shifted this over. Okay? So it was easy to fill in a table because this is a shift register. Now, what about our output? Well, there's 2 patterns I'm looking for. 0, 0, 0, 1. So 0, 0, 0, 1. Right? And so, well, X has to be 0, and this pattern happens here. Right, so we have X is 0, and then we have 0, 0, 1. Okay, or the other pattern, which was a 0, 1, 1, 0, happens here. So those are the 2 places where I'm going to output a 1. Okay, so now that I have my state transition table, then I can make my I can run Moore's algorithm, right? So my first task is divide the states by their output. So what's my first partition? Yes.
B and G from all of the others.
All right, B and G have output 1, 0. All the others output 0, 0. Okay, and now we calculate the next groups for each state. Right, so remember how we did this? A goes to A and E. A is in 1. E is in 1. C goes to B and F. B is in 2. F is in 1. So we do this. We just indicate the groups of the next states. Okay, and now I have to I'll have to look at every group and see if it needs to be broken down. So what does my new partition look like? No one else? Sorry, Claire. Okay.
Look, I just want you to know I'm paying attention.
Yes, I got that.
A and H would be together, and then E and F would be together, and then C and D would be
Okay, right. So now we have pairs of states. Okay, and we do this again. Okay, now I have 4 partitions. Okay, I'll just do it. All right, and that's the next states. Okay, are we done? No. Okay, so what happens now? Yes. Okay, so A and H split and B and G split. Okay, now it's getting a little tedious, but you know, one of our saving graces is once a state's by itself, I don't need to figure out what the next groups are. So I actually only need to check group 3 and group 4. And fortunately, they don't split. They still go to the same next state groups, and so I'm done. Okay. So at this point, I know that states C and D are equivalent, and states E and F are equivalent, and everybody else is different. So now I can change my table. Which states should I get rid of? Yes.
D and F, because we get to choose arbitrarily which ones are matches, but those two are on the right, so
Okay.
those are probably the ones you already animated in your slide.
That's correct. I got rid of D and F. Okay. It doesn't matter. You can get rid of C instead of D, and you can get rid of E instead of F. Okay. All right. You want to do one more, or should we just skip it? One more? You want to work it out on your own? Yes? Okay. Should I play the Jeopardy song? No. Okay.
Wait, what? Which Japanese song?
No, Jeopardy.
Oh, Jeopardy! I was like, what Jeopardy?
Let's see. I'm tempted here.
Oh no, the projection is gone.
Oh, whoops. All right, that wasn't too good an idea. Okay. All right, I'll come back. I guess you need that. Turn on my phone. No? There you go. You see that? No? Okay, enough. Stop.
I forgot all that. I got to step 4 and then I realized G existed.
Oops. All right, so how many people are done? No, that's not good.
Look, glancing up and down takes a while.
I see.
Do I restart or do I try and integrate G into my previous results?
Okay. So, all right, shall I count down? 10? Who's still not done?
I'm doing it as fast as I can.
Oh. So those are you watching the video, you may want to fast forward. No? Yes, yes.
Oh, excellent. Okay, I've got it.
Ready?
Just need speed running it.
Who's still not ready? Oh. Okay. I'm gonna go. I'm gonna count down. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Okay, let's go on. All right, so what's the first partition?
Output.
Okay, E is the only one that's different, right? So this may take a while because he's the only one that's different. Okay, so our next states, these are our next groups, and so now A and F are different from the other four. Okay, I can stop figuring out E because E's not going to get any smaller. That partition's not going to be any smaller. And so I do this again, and A and F are still together. But this one is going to split up some more. So you think we're done? No, because now A and F are splitting up. So A and F were together because C and D were together, but C and D are no longer together, so that makes A and F split up. You think we're done? Nope. Okay. So we split up A and F. We do it one more time, and this time we figure out that B and D are going to remain together, and C and G are going to remain together. So we're done. It's possible that the end of this process, every state is by itself, in which case you had the minimum number of states to begin with, and you showed that it's minimum. Okay, so we're done, and we're going to get rid of D and G and modify the table. Okay, all right. Any questions on this? The notion of equivalent states. There is another way to do this that you may have learned in computational methods that involves a grid, and it's a little less writing. It's not technically more efficient. However, it's not possible to see where you went wrong because you're marking and crossing out a grid, and you look at the final grid, there's no understanding of how you got there. So instead, this method we can see the partitions, and if there's a step where if you make one misstep, we can find it. Okay. All right, so I'm going to change topic entirely now. we're going to go back and talk about timing. So almost 3 weeks ago, no, 2 weeks ago, we introduced the D flip-flop. And we told you the D flip-flop works as follows. At the clock edge, the rising clock edge, it will sample whatever value is on its D inputs, and it will assume that value after the clock edge. But there was a big caveat on this, and that was that the D input has to be stable at the clock edge. If you're changing D, if there's a transition on D, right near the clock edge, you void the warranty on your flip-flop. Okay. Or rather, it may not behave as expected. Excuse me. All right, so let's look at that. So the requirement is that the D input has to be stable, cannot change. It has to be 1 or 0, but steady, during a timing window that's centered right at the rising clock edge. And this window has a part that's before the clock edge and a part that's after the clock edge. And these two sections have different names. The amount of time before the clock edge is called the setup time. And the amount of time after the clock edge is called the hold time. So these are not delays, they are requirements. These are things like you must be at the airport 2 hours before your plane leaves. You must stay in your seat at least 50 minutes after it takes off. Okay? So these are our requirements in order for your flip-flop to work properly or for your flight to occur as planned. Okay. All right. So what does this mean in terms of the circuitry? How is this reflected in our circuitry? So this is a general view of our sequential systems. We have flip-flops here, which I've taken the chainsaw to. I split them in half. These are the same flip-flops. They're just cut in half so that we unfold the circuit. And there are some external inputs. If these are really external inputs, then we ran them through flip-flops. If they come from another component that has our shares are clocked, then they're coming from flip-flops too, and we can consider that part of the state, if you like. Okay, so what happens is, well, we get a clock edge. And at the clock edge, the flip-flops will load the values and start sending them out. But this is the hold time, so we want to make sure nothing changes here. Right, we're in this hold time here, so these new values, they should not arrive too soon, because if they arrive too soon, then we will have violated the hold time of our flip-flops. Okay, now I can't do anything about these, because these are external, so these could in fact violate the hold time of our flip-flops, but hopefully it won't be so bad. We'll talk about what we can do about that later. Okay, so we have our clock edge. Things start to come out of the flip-flops, go through our combinational logic, but hopefully they haven't arrived here too early. Okay, and now we're in the middle of our clock cycle, and now these inputs can change, because it's too late to mess up the timing of these flip-flops. So we actually need our combinational logic not to be too fast. If it's too fast, we could have problems. All right, so now they've arrived, and now we're getting to the next clock edge. Okay, so now they cannot change again. Now they have to stay steady. Okay? And that's okay if this combinational logic has all settled, because these aren't, guys over here, the inputs aren't going to change. Okay? They need a clock edge in order to change, and we are not yet at the clock edge. Yes?
So are the setup and hold times a physical feature of the flip-flop?
Yes. So the setup and hold times of a flip-flop are its properties. So you can go out and buy a cheap flip-flop and it'll have a large hold and setup times, or if you want to buy a really expensive one that you can operate at high speed, it'll have smaller ones. All right, so these are, good designers who make flip-flops want to minimize these times because they determine how fast you can run your designs. So people who want to do high performance want flip-flops that, or circuitry that have very small setup and hold times. Okay. All right. All right. So how do we make sure or check whether we satisfy the setup time? Okay. So let's say this is the output of a flip-flop. Right? So the output of a flip-flop could start to change a little bit after the clock edge. Right? The flip-flop itself takes a little bit of time. When we do our sequential timing diagrams, we always make the flip-flop output change a little bit after the clock edge. So that's called the propagation delay, or the response delay of the flip-flop. The flip-flop doesn't immediately change the output. There's just a small amount of time. That's the propagation delay. So the first thing that happens after the clock edge is that after a certain amount of time, again, this is a property of the flip-flop, the output of the flip-flop will change, or may change. Maybe it's not changing. Maybe it's loading the same value it already has. But if it does change, it will take a certain amount of time before it will assume a new value. Okay. Then that value possibly has to travel through the combinational cloud, through the logic. And that involves some delay, right? We looked at how to calculate that. We did the static analysis where we can actually calculate when the output of a combinational network will have settled. And so at this green line is when we know that the flip-flop inputs values are settled. They're there. And this has to occur before the setup time. Okay, so we have the next clock edge, and this green line has to occur before the setup time starts. So the constraint we have is that the propagation delay of the flip-flop plus the longest path through the combinational logic plus the setup time has to be less than the clock period. So those three things have to be less than the clock period. And if we do that, then if we meet this constraint, then we know that we've met the setup time constraint.
Could you repeat to me what DFF stands for?
So this is a D flip-flop. So this is the delay of the flip-flop. Right? The flip-flop doesn't immediately change at the clock edge. There's a small amount of delay. Okay. So we have those three components. So, somebody might say, hey, I give you three values and ask you what the fourth is. So sometimes you know what your combinational logic delay is, and then you can figure out, well, what's the fastest clock speed I can run at? What's the smallest clock period? So you sum these three, and that's the smallest clock period. Or we give you a clock period and the delay of the flip-flop and the setup time and ask, how fast do I need my logic to be for this clock period? Right? If you know 3 of these values, you can figure out the best value for the 4th one. Okay. Okay, so this is an example of when we would meet the setup time constraint. This is an example where we didn't meet it. It means that the inputs might arrive too late for the setup time. You might not get there quite 2 hours before your plane leaves. You might get there only an hour and a half. Now, maybe you'll still get on the plane, or maybe not. It's not guaranteed at that point, so this isn't something you want to do. Or you could miss it entirely. Maybe you could arrive too late and the plane's already taken off. But either way, we haven't met this setup time. Okay, so again, this is a case where these 3 add up to more than the clock period. Right, before this was a less than or equal, and now this is greater than, so we did not meet the constraint. What can I do about this? I can still run my circuit and hope it works right, but the problem, of course, is it may work right when I do it at home, and then I come in and demo and it didn't work on the board, right? Or the temperature changes, or the voltage changes slightly on the board that I'm using. So timing is influenced by a lot of environmental factors. These constraints tend to be conservative in order to ensure that they won't be influenced by small variations. So you do really want to meet these. How do you fix this? Well, there are several ways to fix this. We could slow down the clock. Right? If I make the clock period bigger, then I make it at least this value, then I'm meeting the constraint. I could try to improve my combinational logic, try to make the delay of the combinational logic smaller. Or I could try to find a better flip-flop which has a smaller propagation delay. Yeah? The setup time and the hold times are property of the flip-flops you get. So, yeah, and the delay of the flip-flop. Those are all properties of how you built your flip-flop. And if you build it carefully, you can try to minimize these. Okay. All right. Any questions on this? So this is setup time. People tend to understand setup time pretty readily. Hold time is a little bit harder to get a hold of.
I get why there needs to be some hold time.
You need some hold time, okay. All right, so here we are meeting the hold time constraint. This means that the flip-flop input did not change until this green line, and that was after the hold time expired. Okay, so there are 3 components that we worry about here. The delay of the flip-flop, now it's the fastest path through the combinational logic that is the problem, not the longest path. So if you have a path through your combinational logic that allows an input to cause an output to change very quickly, that might violate the hold time. But if even the shortest path through your logic plus the flip-flop is greater than the hold time, you're okay. Okay. All right, here's an example where we didn't meet it. Okay. You notice that the clock periods doesn't really matter what the clock is here. I can make the clock shorter or longer. It's not going to fix the hold time at all. It doesn't affect the hold time. Okay, so in this case, it's possible for an input to arrive too early. And this could cause the flip-flop to oscillate or not hold its value, not latch the correct value. All right, how do you fix this? There are only two ways to fix this. You could buy a better flip-flop with a smaller hold time, or you could make your logic slower. Now this seems counterintuitive. Why would you ever want to make your logic slower? Well, you need to, because basically you have a race with the flip-flops. When your clock comes, the outputs of the flip-flops start to go through your logic, and they need to not come back too quickly. You want that flip-flop to be locked up before they can get back to it. Okay? So slowing down your logic may be necessary. Okay. All right, so those are the two constraints. Again, if we give you two values, you can figure out what the third needs to be, or what the constraint is on the third, right? All right, so let's talk about slack, because in lab 6, you're going to run a timing report, and it's going to report slack. It's not going to report delay. It's going to tell you how much slack you have. Okay, and so what does it mean? Well, what it's doing is it's looking at the timing constraint, right? So this was the setup constraint. We needed the clock to be greater than or equal to this value. So it's going to take the difference between those two. Remember, okay, so wait. So this is the same inequality as this one, only we've taken this and subtracted it from the clock. Okay. If this is positive, great. You're meeting the constraint. If it's negative, you're not meeting the constraint. It means that all of these delays together are more than the clock period. Okay, so it'll say worst negative slack, because you don't want any negative slack. You want your slack to be most zero. At least, right? At least zero. And then it'll tell you the most negative one. But you won't have a negative one, because everything, I have yet to see a design that didn't meet timing. Okay. Again, we do the same thing for the hold slack. Okay. Yes? That's what it would mean, yeah. That means you have to fix it. Yeah, so you don't want it to be negative. Well, you don't know. Might not. Those flip-flops might not get the correct value. Right? Your logic might not settle in time. Whenever you design these things, you want a certain, buffer, shall we say. You don't want to exactly meet the constraint. You want to over-meet it by a certain amount of time, just to cover any issues with estimates that aren't exact, or variations in chips, things like that. I remember years ago we had a lecture by an engineer from Sun who explained they had a problem with their Sun workstations not behaving in some African country because it was so hot. Okay.
Because they weren't fully
well, okay, they might have been synchronous still, and yet they didn't estimate the constraints, right? Correctly, or didn't anticipate. Okay, all right. So we've been talking about flip-flops, but you can also talk about hold time and setup time of just an arbitrary component. So if I have some component here and it has a clock input, and I can tell you, hey, this is a hold time and a setup time, and when we do that, we're talking about with respect to when the clock arrives at the component. Okay. Now, if we look inside, the clock actually has to travel inside and probably go to some flip-flops. And so what's happening here, it's translating the time of these constraints and adjusting it according to the delays, which gets you something interesting in which a company might tell you, hey, I have this component with a negative hold time. That sounds strange. Okay, so what's happening is that the inputs take so long to get here that you can actually change them very soon after the clock, because they won't make it here until the real hold time has expired. Okay, so in fact, if you go look at the data books for the Xilinx chips, you'll see that they have a negative hold time. Okay, never mind. But it's actually in reference to when the clock hits the edge of the component, the logic block, not the actual flip-flop. Okay, all right. So we have our rules from synchronous design, and those are so that we can actually go and analyze these constraints. That means that all of our logic is going to fall into this mode. There are no loops in here. All the loops go through flip-flops and come back. So we can check that we meet the hold time and the setup time. Okay, and all we need to do then is analyze this circuit and figure out what the worst delay is for this circuit, or the smallest delay is for this circuit. Okay, if you have a combinational loop, that requires much more analysis, and then timing starts to affect the values that you get and whether it settles at all. All right, any questions on this? I have a lot of time left. No. No questions? No. Yes. You were thinking of asking a question, but you decided against it.
It's off topic.
What?
It's off topic.
Well, I'm done talking about this.
I mean, if there's no questions,
Yes?
this lecture overlaps with the lab immediately after it for me, so I'll run. If there's no questions.
No questions. No questions on lab 4.
I mean, my
No?
lab 4 is not working, but it's also not the sort of thing I can ask a question about.
Oh.
Something's not wired up somewhere, so.
Okay, try to simulate the whole thing together. Okay, so it's a good idea to maybe just simulate your state machine by itself once or twice, but you're controlling all the inputs, and you aren't reality. And so once you get a certain degree of confidence on your state machine, just simulate the whole top level together, because then you have the counters and interacting and the LEDs interacting with your state machine. And the problem could be the result of an interaction between one of them, not a problem within one of them. Right? So until you simulate the whole thing, it doesn't mean you don't know it's worked. So it's not unusual for me to go help somebody and they tell me, oh, I simulated every component, but the whole thing doesn't work. And that could very well be. You need to put them all together and simulate them all together. QSEC and DigSelect are a whole lot faster in simulation because we don't want you to have to run the clock a few million times before you even get one QSEC. So it's
By the way, what do we wire DigSelect up to?
your ring counter.
Our what?
Your ring counter.
Your ring counter. Oh, I see.
You still have
Different speed than the other clock then?
the DigSelect is the right speed for the digits.
I see. I just had the regular clock hooked up to my ring counter.
And that worked for you?